t minus 0 equals, and then the integral of 1 over u du, right? With some stuff out front. Do you remember what stuff was out front? Or had we not simplified it yet? Tell you what we're going to do. We had the integral of m over mg minus cv dv, right? Since I know a lot of you are still new to this, I'm just going to walk it right from here real fast, just to show you again how this kind of works. We had our limits from 0 to v. So u sub starts by finding something to use for u. In real u sub, like what you guys will have to do in calculus where it's hard, you might try 3 or 4 different things for u until you find one that works. You BC kids, is that right? But sometimes the first thing you choose doesn't work out, and you have to try something else. So don't think there's like a magical approach here. Except that in this class, it's almost always going to be whatever's in the denominator. Almost always. So try that first. If that doesn't work, try something else. But it's very likely that that's going to work. When I say very likely, I don't think I've encountered a problem on the AP exam where that doesn't work. So is that kind of coming in for you guys loud and clear? Good. So the next part of this, we must take the derivative with respect to the variable that's being used. I'm saying that carefully because it doesn't have to be about v. It could be about anything, depending on what our problem is about. So I'll take du dv, which is going to give me 0 minus c. Now, you need to solve this for dv, and that's because we're going to replace dv in a few minutes. So I'm going to cross multiply and get that dv equals negative du over c. So now we substitute. And if you truly do this the way you're supposed to redo your limits as well. I don't do it that way. So all I'm going to do is kind of forget about the limits for a minute. Just forget about them. Put in all the things that we have. Now, I would encourage you at this point to take anything that's a constant and take it out of your integral. And we do have things that are constant. M and C are constant, so I take them out of the integral. And I'm left with 1 over u du. That's u sub. What you should be left with is something that you can integrate. Now, you A-Bers, you might not recognize that this is something that you can integrate. And that's okay. Everybody that's in BC knows that this is no big deal. So from now on, this is no big deal. You should memorize, and I do mean memorize. You will have to for calc anyways, that this antiderivative with respect to u is the natural log of u. And you're supposed to put the absolute value bars there when you take this integral. In our class, it's a little meaningless because everything we have will always be positive anyways. But it's always best for you to do what you're told. Okay, any questions to this point? All right, so we're going to do that as our integral. Now, I'm going to hit pause. So, I'll get negative m over c times the natural log of u. Now, it's at this moment that you go back and take what you did for your substitution and put it back into your equation. So now I'll get negative m over c natural log of mg minus cv, and that equals t. There it is. You have successfully done your first u sub and successfully done your first inverse antiderivative. Give yourselves a round of applause. You've been fabulous. Lamest round of applause ever. And trust me, Having received a lot of lame round of applauses, that one ranks as one of the worst. So I appreciate that. All right. Now, I would love to tell you that you're done. You are not. I'll remind you what the whole point was. The whole point of this was to find v as a function of t. But what we have is t as a function of v. So now you have to solve this for v. So, I don't remember. And I told you this was very mathy. You got that, right? Whole lot of mathy math in this. So t equals negative m over c, natural log of mg minus cv. So let's do the long process now of solving this for v. Oh, wait, we can't. You know why? Mr. Shelton skipped a step. I know, I'm such a horrible person. I forgot that we never put in our limits of integration. And we must. We must, they say. So, if you don't remember how to do this, you put in your first limit, v, and subtract your starting point, which was 0. Now, I'm baby stepping it through the next couple of parts because my understanding is that students haven't seen their logarithm rules in a long time. And because of that, they might need a bit of a refresher. Because if we want to solve for v, it's not easy to get it out of here, and there are some tricks to make it easier. And the first trick is whenever you have a sum or a difference of logs, you should combine them. It will make your life easier. So we're going to combine them, and you should remember how to combine them. Whenever you are taking the difference, you divide with the first one on top and the second one on the bottom. Because they're exponents, so you treat them as if they're exponents. You use exponent rules on them. Okay? Remember, negative exponents are in the denominator, positive exponents are in the numerator. That's why the mg goes in the denominator.
Wait, is that minus C?
It's minus CV. You're just reading it wrong. I believe you.
So you plugged in, like, to subtract the limits, you put 0. Where'd you plug in with v?
I plugged in the v where the v was.
But it was already there.
I know. We remember integrating the velocity. I could have said that this was like VF for final velocity, if you'd like. Will that make it easier to understand? Okay, so it's VF for final velocity. Our initial velocity was 0. Okay. All right, ready to keep going? All right, now you need to get V by itself, or in this case, VF by itself. Now, please understand that what we're doing right now isn't really physics. It's just mathematics, but you'll have to do this on the exam. So I'm going to keep going. The first thing I want to do is I want to get the logarithm by itself on one side, because that way I can get rid of the logarithm by using the base e as my way of getting rid of it. So I'm going to multiply both sides by negative c over m times t on the left side, and then I'll just get the logarithm by itself. Everybody okay so far? I know, this is way boring. I get it. I'd love to liven it up, but nah. I'll move that up to the top. It's as if it didn't exist. And now we're just focused on what's here. I'm going to raise both sides to a base of e. I assume you know to do this, but my experience has been that you need a refresher. when you raise a logarithm to a base of the same, then it just disappears. You remember that, right? Maybe not. I'm indifferent, so if you don't remember it, that's your problem. Now, there's a variety of ways to go from here, but we need VF by itself. I'm thinking of multiplying both sides by mg. You guys all right with that? So I'll get mg times e to the minus c over m times t equals mg minus cvf. I'm not really having to do any more fancy math. It's just algebra. So I want to get VF by itself. So CVF on this side and mg minus mg e to the minus c over mt. Whew. We still doing okay out there in the homeland?
Doing great.
Fantastic. Do you notice you can factor out the mg? You should do so. So I'm going to get CVF equals mg times 1 minus e to the negative c over mt. Yep. This is fun math. I don't mind this. I think this math is kind of fun. Oops. Get out of here. Get your busted stuff out of there. Move you up to the top. You guys can't see that, so there. All right, so only one thing left to do. VF equals mg over c times 1 minus e to the negative c over mt. All right. Did everybody arrive safe with me here? This is a motion equation derived from Newton's laws using the rules for differential equations. You will be expected to do this on the exam. More importantly, you will be expected to do this on your next test. Okay? Yeah. There's two sides to this. First, I was trying to teach you a procedure. I don't know whether you guys were able to write enough notes to yourself to be able to use this procedure in the future. And so I will recap the high points of what was important here. But there's also the result of this procedure. We have produced something actually of vital importance, something that we should study, something that has physical meaning in our world. So there are two parts to this, and that's why I want to be very careful about how we approach this. So there's the process that got us this. But this is a motion equation, meaning dv dt will be the acceleration. Integrating this will give us the position. This is a motion equation and can be treated just like a motion equation. Now, taking a derivative isn't very interesting because we already know what the answer should be. We got this from taking the integral. So you should, though, be able to figure out the acceleration of this guy by taking the derivative. But we'll cover that part in a minute. I want to point out what you should do whenever you're done with a differential equation. You had boundary conditions. We know that at time 0, the velocity was 0. You should always check your boundary conditions and see if it gives you what you expect at the boundary. Meaning when you plug in 0 for t, do you get a velocity of 0? If you don't, you did your math wrong. Either your algebra or your integration. So you should always check. So when I put in 0 for t right here, this entire term becomes 1. And then this whole thing from here to here becomes 0 because it's 1 minus 1. So effectively, I tested my boundary condition. And my boundary condition says that at t equals 0, my velocity is 0. That's great. Now, when you look at this, you do all see a decaying exponential here, right? That at infinity, this value goes to 0. You guys all okay with that? Do you understand what I'm saying? I'll say it again. E to the minus t over m times t. The limit as t goes to infinity for this is going to be 0. You guys, everybody, A, B, and B, C has done this kind of stuff already, right? So I'm not saying anything too crazy. Doesn't matter what C or M is, when t is very, very big, that whole thing is very, very small. Which means that after an infinite amount of time, everything in here becomes 1. Does everybody see why that has to be true? Now this part's important. This is where you really should pay attention. That means V after a long time is equal to mg over c. Now, if you don't understand why I'm putting this in front of your face, remember where the whole thing started. Coffee filter. Falling through the sky, experiencing two forces, mg and cv. When we did the lab, we measured the terminal velocity, the point at which the net force was equal to 0, where mg minus cv equals 0. This is called the terminal velocity. And if we solve for it, we get, lo and behold, mg over c. Do you see why this is an important consequence and something we should check for? We knew that our equation should show that the object approaches terminal velocity after a long period of time. Our equation, we just verified. When we consider t to be a big number, we expect this thing to approach terminal velocity. In fact, I want you to graph it right now in your calculators. What does this graph look like? And look, you don't need any of this. You need to just simplify it all out. All your graphing is 1 minus e to the negative x. Get rid of all the constants. You need the shape of this graph. But I can't remember. So I assume you guys have all got a graph now that you're looking at. You have an idea of what that graph looks like. So if I was to graph it, would you agree that first, I'm putting velocity here and t here. At time 0, we know it starts here. And you have a graph that kind of is asymptotic. Is that what yours looks like? It should. You will almost always be asked to graph this. Almost always. And you should be able to not just graph it, but indicate where the asymptote is. That's where our asymptote is. When you put it in a graph, you just did 1. But your asymptote is at 1 in your graph. But that's scaled by what we pulled out front. If you're asked to graph it, this is what they expect to see. The shape of the graph and where the asymptote is. So our object actually never gets to terminal velocity, apparently. And if you're really, really good at math, and I know a lot of you are, then you should be paying attention. This combination controls how fast the object gets to terminal velocity. That's what really controls it. And if you did the lab, you know that the more massive the coffee filter was, the longer it took to get the terminal velocity. You know that from the lab because when you were dropping it, you had to wait longer and longer on your graph to be able to figure out where you could take the slope, because it took longer and longer to get there because it was heavier and heavier. Terminal velocity was faster and it got further away. Now, to answer Luke's question, they will expect you to be able to recognize this formula, and you might be expected to pick it out from a list. They will present you with several examples, and you'll need to know which one matches an object approaching terminal velocity. This terminal velocity formula is not on your equation sheet. I wouldn't spend a lot of mental faculty committing this to memory. I would come to recognize what this term does to any formula you're going to have. This is an exponential or an asymptotic exponential formula, meaning it's going to approach some asymptote exponentially. We're going to see about 2 or 3 other formulas like this. You should be able to come to grips with what this is, where it comes from, and what it means. Now, I'm going to stop for a minute there for you. It all starts generally with Newton's laws. So you start with a force diagram and Newton's laws. Newton's second law is the typical place that we go, because we are likely to have a force that is velocity dependent. So step 1 is create a Newton's law formula. For us, that was mg minus cv equals ma. Now, use Newton's second law. The reason? Because it's got a differential in it. The A is already a differential that's built in. Because that's step 2. Replace A with dv dt. Next, you've got to split your derivative. You have to split your derivative. That part wasn't so bad, but it did mean having to do a little bit of algebra. For us, that meant dt equaled m over mg minus cv dv. Step 4, set your limits. Boundary conditions. And integrate. So, usually your boundary conditions will be pretty easy to deal with. It's almost always for time going to be from 0 to some point in time. And almost always for the velocity, it's going to be an initial velocity and a final velocity. We dropped the coffee filter, which is why our initial velocity was 0. Don't assume it's always 0. Sometimes your system is slowing down. So, step 5, though, is compute your integral. You got to compute your integral. You know, for us, that was not easy. Can't remember exactly. Was it mg times the log of mg minus cv minus mg? Was it like that? I can't remember. I'm trying to put them all. I think I made a mistake. I don't think this is there. I think it was M over C with a negative. Yeah, that's it. Okay. Computer integral. And then generally the last step is solve for, and it doesn't have to be V, but almost always it's going to be velocity or position. We're making a motion equation. So this is motion of an object in a resisting medium. And this is one of the easier of the examples. If you get an example, you hope it's going to be this one. Trust me when I say the moment we have one where the drag force is CV squared, it gets harder. It's harder because your U sub doesn't work as well now. So this was the easiest example I could offer you. I know that it had a lot because it had that, it had all that stuff with the logarithm in it, but it's actually relatively easy. This is the process though. Now getting back to the actual physics here, consider this for a moment, and I'm going to turn you guys loose on it because I need you to work a little bit, show that you're actually awake. But I'd like you to tell me what the acceleration looks like here. Before you figure it out, you already should know that this acceleration has to get smaller and go to zero. Remember, when the object first is released, what is the acceleration of the coffee filter at time zero when you first let it go? You should expect that your derivative will have the principles that the acceleration at time zero will be g, and the acceleration after a long time will be zero. You have an idea of what your answer should look like. All right, get busy. Find me the answer. What is dv dt going to look like? So first things first, I'm a realist. Take the derivative of mg over c, that's just zero. So let's go to the next part. When I want to take this derivative, well, I'm going to have to chain rule it like twice. So mg over c is going to be out front. Now I need to take the derivative of e to the negative c over m. And the derivative of e to anything is just whatever it was. But now I take the derivative of this part. The chain rule is like. I'm taking this derivative with respect to t, so c over m acts like a constant in front of t. So it'll be negative c over m t to the 1 minus 1. Which goes away. Now, I can clean this up because I have an m here and an m here, a c here and a c here, and the negative times the negative makes it a positive. So my answer is g e to the negative c over mt. Let's check to see if it fits my requirements. At time 0, this entire term is 1. That's good news, because that means at time 0, the acceleration is g. All right, so at time, long time from now, infinity, this entire term goes to 0. It's great. It's exactly what I thought it would be. So what does this graph look like? I'm not joking. I want to know what this graph looks like. This one you might not need your calculator for. But if you do, go ahead and put it in there. Just e to the negative x. Yeah, it's decaying exponential. It's no big deal. When asked to do this on a test, you're not just going to be able to put this and be done. That's not okay. Because we know that this actually begins at G. That was our boundary condition. It's not an asymptote. The asymptote's 0. But it starts and crosses the axis at G. And they'll be looking for you to identify that. Now, just for funsies, ours was negative. So when you did this lab, you tended to look for a portion of the graph that was linear. But it looks something like that, where there was a section where it was accelerating and a section where it had a constant velocity.